So for arbitrary algebras, this is still quite horrible when you actually work it out for specific examples. But nevertheless, I think it's a fairly clear path on how to solve this. Now, you could say, well, who cares? You already had a way easier path. You told me earlier today the matrix exponential. I mean, the matrix exponential solves the thing, so why not just stop there? Because I want to understand it, I want to understand how the arguments that we give in differential equations generalize in different directions. Because I have found that doing that gives me insight that I didn't have before I did this. So I don't want to find one general solution. I want to find all of the general solutions that are related to the ones that we're familiar with in the course. So. All right. So my goal for next time, man, we keep getting hit on the holidays this semester. Like Monday and Wednesday are bad. So we lose Easter Monday, don't we? But hopefully by next Wednesday. So if you think of questions, so if you'd email me your questions, Jess, that would be helpful to me. I can try to take those and create maybe sort of a playbook for where we should go forward, like trying to piece together basic. That would be a fun realm to jump into. I do. Yeah, I want to do in here. I want to do like a crash course in linear algebra over a ring. I think that would be productive.
I was looking at other stuff to see which one I thought would hold, and it would be too bad looking at. I think everything in the spectral theorem is good. I think everything is fine there. I think it's really, but just like looking at it, I didn't think it would be that interesting anyway, even if it wasn't. I mean, I think it was fun. Yeah, just the Jordan Form stuff. And then I also found something, since I wondered if it was a topic for the algebra course. Apparently there's something called Jordan-Chevalier decomposition.
Mm-hmm.
And I was thinking
the Jordan-Chevalier.
I was just starting to look into it when I ran out of time.
Uh-huh.
But I was going to look into something, whatever that's about. But that
It
also talks about like nilpotent elements.
You know,
and I was wondering what it would look like for nilpotent elements.
We haven't done much with nilpotent stuff here, have we?
Which I think would be interesting if we were actually talking about like the null numbers.
We could try to do some example with null numbers, see what happens to us there.
But I feel like that
solutions tend to get polynomial.
Yeah.
They're not too bad, actually. Hehehe.
I didn't really finish looking into that, so I don't know what the Jordan-Chevalier decomposition is.
If you just shoot me an email with some of your random musings, that'd be productive. It'll help me remember to do it. I'll pin it to my stack, and Here's a question, King. Can we reverse engineer what I'm doing right now to get a sort of analog to the Jordan form? So my way of understanding the Jordan form, I taught differential equations before I taught linear algebra. So I became aware of the generalized eigenvector solutions as a means to solving differential equations. Then, personally, I studied Jordan form, more detailed than linear. So for me, I kind of reversed engineered the process. For me, understanding how to solve a differential equation has given me insight into linear algebra. Sort of the tail wagging the dog in some sense, but maybe we could make that, maybe that could be productive here. See, because this strategy that I've just outlined could be turned on its could be turned on its head to suggest the existence of a basis for the original problem in which that matrix has a specific form. I'm not overly optimistic for it though, because the thing that's going to keep it from being nice is exactly this trouble. Filtering that back up to the original to find a kind of a special, not an eigenbasis, but some kind of other basis. There's a fuzzy idea that I have. So my idea is, we've discovered something nice at the level of the extension algebra, right? So can you take these different things, the V0, the V1, the Vn minus 1, can you use those as a basis for your original problem? When you look at the original problem with respect to the basis built from, let's think of this as being dr d zeta equals to t of r. Okay, so what if we take that t of r and we recast it in terms of the coordinate system using these v0, v1, vn minus 1 as the basis? I can tell you what happens in the real case. When you have when you have a complex eigenvalue for a real transformation, and you change to the basis a comma b, what happens is the matrix of the transformation becomes manifestly a dilation times a rotation. So it doesn't diagonalize it, but it does something rather special. It reveals that that linear transformation is actually a rescaling and a rotation if it's got a complex eigenvector in the plane, eigenvalue in the plane. So it's conceivable to me, maybe not for the general case, but maybe for specific choices of algebra, we could gain actually insight by looking. Let's dial it back a bit, not try to do the absolute most general thing. Pick something specific like hyperbolic numbers. Ask the question, for the hyperbolic numbers, for a system, when you translate back the basis for the extension, what does it make the original matrix what does the change of basis do? That might actually be an interesting question. Let me try to reformulate it. I've told you that so you can think about it, but okay. Anyway, the janitor will soon be upon us. Let's go.